So today, we're going to build an AI that can read handwritten numbers, but we are not stopping there. Oh no, we're going to break it on purpose. Why? Because performing an autopsy on a failed AI is honestly the single best way to understand how it actually thinks.
So yeah, let's get our hands dirty. Think of this as a detective mission into the digital mind of a machine. Our goal isn't just to build something that works. It's to figure out precisely what happens, and more importantly, why, when it all goes wrong.
I mean, really think about it for a second. Your brain's visual system has been fine-tuned over millions of years. It looks at an image like this and just knows. It's an absolutely incredible feat of biological computing. But for a machine that's starting from absolute zero, learning to see is one of the biggest challenges in all of artificial intelligence.
Okay, let's dive right in. First things first, we need to build a basic neural network. You can think of this as our initial suspect. It's simple, maybe a little naive, and honestly, the perfect place to start our investigation.
And don't you worry, you're not going to need some supercomputer or a PhD in advanced mathematics. We're just using standard, totally free tools that literally run right in your browser. This is all about getting the intuition, not getting bogged down in complex equations.
So, here's our plan of attack. It's super simple, really. First, we've got to get our data ready for the AI. Then, we'll actually construct the brain of our model, and finally, we'll hit the big train button and just see what happens. You see, an AI doesn't see images like we do. It only sees numbers. So before it can learn a single thing, we have to translate every last pixel into a language it can actually understand. Just feeding it a raw image, that'd be like asking it to read a book in a language it's never even heard of. It just wouldn't work. And this really comes down to 3 key steps. First, we normalize the pixel values. We're just scaling them down to make it way easier for the network to learn. Second, we reshape that 2D image into one long list of numbers. And finally, we one-hot encode the labels. Now that just means instead of telling the AI, hey, this is a 7, we give it a list where only the 7th spot is turned on. It gives the AI a perfectly clear signal to learn from.
All right, so we've followed the plan, we've launched the training process, and something is very, very wrong. Our digital brain is broken. Now the real work begins. It's time to examine the crime scene.
Just look at this graph. After a tiny little initial jump, the accuracy line just goes completely flat. The learning, it just stops. Our AI isn't getting any better, it's just stuck in a rut. This flat line right here, this is our first major clue.
Now our culprit has a name, and trust me, it's one of the most famous villains in the entire history of deep learning. We, my friends, are dealing with the vanishing gradient problem. Let's start the autopsy.
So what does that actually mean? Well, in a deep network, one with lots of layers, the feedback signal that tells the network how to get better gets weaker and weaker as it travels backward through all those layers. By the time it reaches the first few layers, the signal is basically gone.
That analogy is perfect. The instructions for learning, that's the gradient, they start out strong at the very end of the network. But as they get passed backward from layer to layer to layer, they just fade into nothing. And that means the most important early layers, the ones that are supposed to be learning the really basic stuff like lines and curves, they get no instructions at all. And so they just stop learning.
And here we have it, the perpetrator and the hero, side by side. The problem is this thing called a sigmoid activation function. It squishes its output, and when you multiply these tiny little numbers over and over again in a deep network, the learning signal just dies. The fix? A function called ReLU. It is incredibly simple. If a signal is positive, it lets it pass right through. If it's negative, it just blocks it. And that simplicity is what allows the learning signal to flow freely, solving our mystery.
Okay, diagnosis complete. Now it's time to perform the surgery. We're going to go back into our code and engineer a much, much smarter, more resilient network. So, our fix has 2 main parts. First, the easy one. We just swap out all those problematic sigmoid functions for our hero, ReLU. That takes care of the vanishing gradient. Second, we're going to add a clever new technique called dropout. This is a trick to stop the AI from just memorizing the training images, instead of actually learning how to generalize to new ones it's never seen before. Think of it this way. During each training cycle, dropout just randomly turns off a few neurons. This forces the other neurons to learn the features more robustly because they can't rely on any single neuron to do all the heavy lifting. It basically builds a stronger, more flexible team that doesn't just memorize one set of plays.
Okay, so our model is fixed and it's learning beautifully now. But there's a deeper, more fundamental flaw in how we even started this whole thing. We've been forcing our AI to see the world in a way that just isn't natural for images.
Remember that reshaped step from way back at the beginning? We took that nice, square 2D image and we just flattened it into a single long line of pixels. What information do you think we destroyed when we did that? We lost everything! All the spatial structure, the shapes, the edges, how pixels are neighbors with each other, it's all gone.
This is the modern solution. Instead of a dense network that only sees a flat list of pixels, we use something called a Convolutional Neural Network, or CNN. A CNN is designed from the ground up to see an image the way we do, as a 2D grid. And this lets it learn important spatial features like edges and corners, making it unbelievably better for any kind of image recognition task.
So, we've upgraded our model to a modern CNN. We've trained it up, and yeah, the results are pretty darn impressive. But the case isn't truly closed until we analyze its final inevitable mistakes.
99.4% accuracy. That's fantastic. I mean, out of 1,000 images, it only gets 6 wrong. It is so easy to stop right here, declare victory, and call it a day. But that's not where the deepest insights are hiding.
The real story, the most valuable data, is lying in that tiny little fraction of errors. Why did the machine get those specific images wrong? What can its mistakes teach us about how it actually perceives the world?
Because when you actually look at the images our final AI got wrong, a 9 that kind of looks like a 4, or a 7 that looks a lot like a 1, you realize its mistakes are often very human. They aren't just random failures, they are little windows into its logic. So the next time you see an AI fail, don't just see an error.